So in the last class, we tried to study electron motion in the crystal. And remember what we emphasized, that actually to understand the electron motion at a very, very basic level, we need to understand the competition between the hopping and the Coulomb interaction. If the Coulomb interaction is very strong, dominates the hopping, then every electron is trapped on its own atoms. And then the things became like a insulator. So that's a kind of multi-insulator. However, if interaction are weak, but the hopping is strong, then we can ignore the interaction. And the electron hopping from one atom to another atoms will make electron move around. And then we'll get a conductor. So that's a zeroth order approximation. So now we want to assume, let's assume interaction weak, hopping is strong. Okay. Certainly in the real crystal, the interaction is never weak. They're always same order. But there's a saying, 3 is infinity, 1/3 is 0. If interaction weaker, the effect is not very strong, so let's make that equal to 0. So we consider the free system. So actually, a lot of condensed matter theory are built upon this free electron system, although in the real material, interaction about the same order. So we'll follow the tradition. And so we do this. So now we do the free system. And then we try to understand how non-interacting electron moves in a periodic potential. So what we managed to obtain is that we have some kind of plane wave. We build some kind of plane wave states. We say that this kind of plane wave states actually is the energy eigenstate of the hopping Hamiltonian. And then from there, and the energy eigenvalue for this plane wave states actually is function of a k. So it's epsilon k. And we get so for every plane wave state is a eigenvector, and for every eigenvector we get eigenvalue. So therefore we get the dispersion relation, the relation between the wave vector k and energy. Then we claim that knowing this, we kind of know how electrons move around, because near the minimal of this dispersion relation, the dispersion can be something like that. But near this minimal, so this is a epsilon k, so this is a k. Near the minimal, we can have this minimal value, which appear at maybe at a p minimal. Then we can expand around the p minimal. This get a plus 1. There's some effective mass, which is curvature p minus p minimal square. Okay. So we just expand near the minimal. Then near the minimal, we get the quadratic dispersion relation. So the energy goes like 1/2m times momentum square, except it's get shifted. Okay. And so this is very similar to the energy momentum relation of a particle in the free space, except that this mass gets changed. So we claim that the particle, at least near the band minimum, behave like a particle with mass m. Then we apply Newton's law for mass m particle, F equal to ma. Then from there, we try to get how particle move around. So that's basically the idea. Yes?
Is there a possibility that the dispersion relation goes like k to the 4th power or something like that, such that the mass is 0?
Yeah, it's possible. You can design a band where this m equal to infinite. So this term don't appear. The leading term maybe is a p minus p minimum 4th power. It's possible, it's entirely possible. And thank you for your question. And that's really the motivation for our next discussion. You know, what's going on? You know, if a dispersion relation is like this, we don't even have a mass. You know, how we apply Newton's law, F equal to ma. So actually, the problem is much bigger, actually. So So from here, what we have is not a mass. We have an energy K relation. We have a dispersion relation. We don't have a mass. So we need to formulate Newton's law without a mass. We don't have a notion of mass. Actually, mass is an approximate concept. It's a concept near the bottom band. If bottom band have other behavior like this, we don't have a mass. If a particle is here, for example, have very high momentum, there is motion. We cannot. There's no such thing as a mass. We just have some kind of function. We don't have a mass. So we need to generalize Newton's equation to the situation which we don't even have a mass. And so how we do that? And also we can say, how do you get F equal to ma? Who tell you that? This is not a particle in free space. This is a particle in the periodic potential. There's no such thing as F equal to ma. And so if you believe for the particle near the bottom band, the F equal to ma applies, you have to show me. How do you show that? Why the motion of particle near bottom band follow Newton's law? If you can derive that, maybe you can see how to generalize that. So that's really the question. So there's no such thing as F equal to ma, actually. We just have a dispersion relation, we know nothing. And we try to derive, what's going on. What is the motion? What is the motion? It turns out that even near the bottom band, the Newton's law is not valid. There are corrections. So actually, even in the bottom band, when a particle do have a mass, and Newton's law is still not valid. So therefore, the motion of particle in a semiconductor or in the material is quite interesting. It don't obey Newton's law, but obey a generalized Newton's law. Okay, so this is the motivation for our next discussion. Why? So that's what the problem in our mind. But to do this, to carry out this calculation, we need to review this Lagrangian formulation of classical mechanics. And the reason we want to do that is the following. What we try to do here is we want to go from a quantum theory to a classical theory. So what do you mean by that? Okay, what I mean is what I do here is a quantum theory. Remember, this eigenvalue is obtained by diagonalizing this big matrix. When you diagonalize this big matrix, it's a quantum theory. So those just this plane wave just amplitude for the energy eigenvector, amplitude for each on the basis. We just diagonalize big matrix. That's quantum theory. But what we want to get? We want to get the equation motion. But the equation motion is not Schrodinger equation. We already know Schrodinger equation. We want to obtain a classical equation motion, something like Newton's equation or generalized Newton equation. So here what we try to do is that we want to derive a classical equation from a quantum theory. And we know the classical equation is not correct. It's wrong. So we want to derive something wrong from something right. Quantum theory is right. And but classical equation, why we want to do that? You have a perfect quantum theory. Why you want to derive a wrong classical theory? We don't have to. But we are classic animals, actually. When you have a classical equation, we feel very happy. We can see what's going on. When you have a quantum big matrix, we just don't know what's going on. So therefore, here this really what I try to say is what we try to do is a classical approximation. To obtain some intuitive understanding of this big quantum accurate exact quantum theory, we want to obtain approximate classical picture, classical approximation. But a classical approximation is more intuitive because it fits with our culture. We learn classical physics first. So when we see something classical, we feel we understand. And although it's approximate. And so this is what we try to do. We try to obtain a classical approximation of quantum theory. And the tool we are going to use is actually the Lagrangian. So we'll describe a very general way to go from quantum to classical. Although this method apply for this, we are going to apply this method for this motion for particle in the band. But actually, the idea is much more general. I think last week you derived this spin wave. Actually, you can use a similar idea from quantum description for magnets to the classical spin wave equation using very similar idea. So this to obtain the classical motion from quantum theory is a very powerful way to gain some very direct picture for quantum system. So let me review this about the classical equation, the Lagrangian formulation for classical equation of classical motion. So so first, I want to say that the most important concept in classical physics is the concept of state. Basically, it's a data you need to characterize a system. So that's a notion of state. If you know a state, that means you have enough information to know what happened to the system in the next moment. So the state is enough information which determine the state itself in the next moment. And certainly you can say, you can try, okay, the position, let's consider particle. A position of a particle is a data. But this is incomplete data. Knowing position alone, we don't have enough information to know what is position in next moment. Okay. So what we need is we need a position and a velocity. And sometimes if you know the velocity, you know the position in next moment. It just shift the x in next moment, just x plus v times delta t. In next moment, it's just that. But you also know what happened. What is v next moment? The v next moment just became v plus f force divided by m times delta t. So here I use this Newton's equation, F equal to ma. Okay, so this is the t. This is t plus delta t. So therefore we know this. We know the evolution. So the point is that but certainly we can. So here we will for the later discussion, we are not using x and v. We'll use x and p momentum using this to characterize the state of a system. Okay, so there's a notion of states. Okay, and once you know the notion of states, then you have this so-called phase space Lagrangian. You can introduce some kind of action, which is a function now of xt and pt. But here I want to emphasize this actually is a function now of so-called the state as function of t. You know, it's data describing state. That's a pair. X and p is a pair of data describing state. The state as a function of t. So you imagine in a state space, you have a trajectory, the time-dependent trajectory. This time dependence gives you a trajectory in the state space. And so that's imagine we have state space xp, and this function, pair function, just give you a trajectory. And for this trajectory, for every trajectory, you get a number out. And that's our action. This is action. Okay, why we do that? Okay, so let me just go one step further. For this, we can always write this action as something, integration of Lagrangian. You know, it's a p and a p dot. You know, it's generally just depend on the position and their derivative. Okay. And so what? And so the point is that this Lagrangian is a data for the system. So what do you mean by that? You know, when you have a state, the state can move around, can evolve. But when the interaction are different, or when the situation are different, the state may evolve differently. So when so in that case, we say we have a different system because we have different interaction, we have different system. So basically, we try to ask how to describe a different system. You know, do you have a data to describe systems? So here we have a data to describe a state, which is x and p. Do you have a data to describe a system? So the system really means equation motion. The different systems have a different equation motion, and state evolve differently in the different system. So you want to have a systematic way to say how state evolve. We want to have a systematic description of a system. And so the formulas I developed here is that this Lagrangian is a function. Actually, this function is a data to describe a system. We say different function have different system. And because different function will lead to different equation motion, and representing different interaction, things like that. And so this became very general picture for classical theory. The state is x and p. That's a point in phase space. And the system is a function in phase space. We have some function in phase space. Okay. We'll come back to this a little bit more. Then there's what is equation motion. So here I promise that for every Lagrangian, you get different equation motion. So that describes different motion. That's a different system. So let's see how the Lagrangian are related to the equation motion. Okay. And this is coming from this action principle. So basically, we want to find, in some sense, we want to find the path in this space, so that this value get minimized or maximized, or it's becoming stationary. Usually, if you change the path slightly, this value would change, and the change will be the first order. If you make a distance epsilon, this change also order epsilon. But there are some particular paths where if you change the path a little bit by epsilon, these s don't change, at least to the linear order in epsilon. The second order epsilon squared may have some change, but there's no linear change. So this kind of a special path is called a stationary path. And this stationary path describes a particular curve, the particular time dependence. So that depends on a particular motion. So that's how we use this function to encode the motion. Certain paths which maximize or minimize this function, that path represent a lot of the motion. And so the function and the motion get linked. So to carry this out, so let's try to see. Let's consider a variation of action. We just have a xt. We just get delta xt. Pt also get the change delta pt, and etc. So something like that. We just plug in. Just plug in this x replaced by x plus delta x. P is replaced by p plus delta p. Then just plug in over there. When you plug in over there, and this is what you get. Let me just copy what we have. Partial L, partial x, delta x, and I'm sorry, I should say it's a delta s equal to this minus s, which only x and p. So this is a bit more precise. And then we have this partial L, partial x dot, then delta x dot. X dot means the time derivative, and the partial L, partial p, delta p, similarly, partial L, partial p dot, delta p dot. So just something like that. Okay, yes? That's right.
In this case, do we fix both the final position or initial and final position and momentum, or just for which position?
Wait, I try to hide that. And so what we try to do is that we just have a path we want to change this path a little bit to see what happens. And then we want to find a particular path such that this little change don't induce anything at the linear order. And certainly, so then you get a condition or equation. But there's many solutions of the equation. That means there's many paths satisfy this condition. So then you have a bunch of paths. They all have this property that a little change don't change action. But there's other bunch of paths. Those are illegal. Those paths in the little change would cause big change. So that's illegal. So this is enough. So once you obtain all the so-called legal paths, then you'll say which legal path fit your initial condition, and that will be the actual evolution with that initial condition. So this comes later. Here we just want to figure out what is allowed motion. Then the initial condition is the boundary condition for this allowed motion. Yeah. And so then we can do the integration by parts. So this time derivative, we can make a dt to here, because this is crucial, because the delta x is kind of local. We only change, it's only non-zero in a small time segment, in some part, but zero in rest place. So we can do the integration by parts. When you do integration by parts, what happens is that this dot became, this sign became ddt here. There's a surface term, but because delta x is only non-zero in the middle, in the boundary, the delta x equals 0, so there's no additional surface term. So similarly, this one can be moved to here, do the integration by parts. We get this. And then we can, collecting term together, we have this. And that's it. Okay. So the computation is a little bit quick, but there's notes you can try to do that yourself. And so the key point is following. You can see this is rather like doing differentiation. You know, this delta x is some arbitrary local functions. Okay. Then the changed cost is another function multiply delta x and integrate. If this function is non-zero, you can always pick up some delta x so that this integration is non-zero. You have a linear part. So in order for the path do not have a linear part, this has to be 0, and this has to be 0. So if these two conditions are met, then we have a path which are stationary, which is either maximal, minimal, or some or in the saddle point. So this is really just obtain these two well-known equation motion, and so this is a so-called phase space equation motion. Okay. So this is a rather abstract, and but let me just consider a special case. Then it became much more illuminating. So there's a particular Lagrangian we want to do. That is equal to p x dot minus Hamiltonian, which is a function of p and x. So we have this particular choice of Lagrangian. Okay, so let's just plug in. If you plug that in, we find the x dot equal to partial h partial p, and the p dot equal to minus partial h partial p. Okay, so this is this is the it's a more standard. It's more like Newton's equation. And to make them even more familiar, let's choose h equal to 1 over 2m p squared plus some vx. Okay. So why is that? So let me just check why is that. So let me see. Sorry, yeah. Okay, so let me see. So the first equation, I think the first equation became p dot. Let me see. Yeah, the first equation became this one because from here you can see this partial L partial x dot equal to p. That's from here. Give you p. Then this partial L partial x dot with a time derivative then equal to partial L partial x. But the x only come here. So partial L partial x gave us partial h partial x. The minus sign here is here. Yeah. And similarly, this the second equation over there gave the first equation here. And yeah, I don't know if you can see it or not. This partial L partial p gave us x dot. So this x dot from partial L partial p. And there is a partial and also, yeah, partial L partially also give this second term. So this we don't have this term. This term is we don't have this term. Just have this term. Okay. And but for this case, and we see that this equation just reduced to the x dot equal to p over m, and the p dot equal to minus partial v partial x. So this is a real Newton's equation. This is a real Newton's equation. Yeah. So this is just some review of a phase space path integral, and we are going to use that heavily later in order to derive this classical equation. And so as another application, and since we are going to use that, and so let's consider okay, how to describe electron in magnetic field. Okay, so here I already say that. So let's come back a little bit. We say in this particular choice, this term kind of fixed is kind of something canonical. So all the choice is this Hamiltonian. If you choose different Hamiltonian, meaning different function of x and p, you describe different system. So that's what I try to say. Different Lagrangian, different system. But here, because we fix this form, now here we just need to choose function for x and p. Different choice of x, p give you a different system. For example, if you choose this H Hamiltonian to be this particular form, what that means? It describes a system of a particle with a mass m moving the potential v. So that's what this equation tells us. Okay, so that's good. This potential v can be this electric potential. When we have a charged particle moving the potential, then they describe this system. This is the mass of a charged particle, and the v would equal to the E times the potential phi. So now let's ask the question: how to describe in the phase space Lagrangian formulation a particle moving in magnetic field? So this is a little bit non-trivial. So how to describe a particle moving magnetic field? So here I would say a charged particle moving in the electric potential is described by this Hamiltonian. But now we have a charged particle moving in the electric potential and magnetic field. So there's a Lorentz force. In that case, how to describe it? Means how do you pick a Hamiltonian so that this particle in magnetic field will be described? So how to pick this? And so it turns out that now we have electric field, which is a partial phi, partial x. And we also have a magnetic field. Okay. So our choice of Hamiltonian must depend on magnetic field. Okay. So, but actually there is something quite funny. We couldn't do it. We cannot write down the Hamiltonian, which in some way depend on magnetic field, and produce Lorentz force. We just cannot do it. We have to using a amazing trick, and even now I don't know why we have to use this trick. And this trick is that we write this magnetic field as a, I'm using the K here. So this epsilon is a total antisymmetric tensor. So this IJK, just a 1, 2, 3, is a space dimension, X, Y, Z. So this is total antisymmetric tensor. So this basically really says that the BZ is equal to partial X AY minus partial Y AX. So first we have to express magnetic field in terms of a vector potential. And then we can do it for some reason. Then we write down some Hamiltonian which depend on vector potential. Then we do it. It's a little bit strange. We have to do this trick. We cannot really using magnetic field. Okay. Certainly there is an issue about which one is more fundamental. Is the vector potential is more fundamental, magnetic field is more fundamental. Equation motion you can written in terms of magnetic field entirely, but somehow the action cannot. And so there are some questions here. So don't worry about that for the moment. So once you deal with this vector potential, then I claim the following works. The Hamiltonian actually can be written as a Pi minus AI squared. The vector potential actually is a function of x over 2m. Then you may have a potential. Actually, this Hamiltonian works amazingly. And we cannot do that using the magnetic field. We have to using vector potential. Yes?
Sorry, Professor. I just don't see why this is so special because the Hamiltonian have to include electric potential.
Yes, the same thing. Right. So we already encountered the same problem. We cannot write down Hamiltonian using electric field. We have to using electric potential. So this became a little bit fundamental in the following sense, because when you have an electric field and magnetic field, how do you describe a situation? We say, okay, we describe electric field, magnetic field, then we describe the situation. That describes our system. But amazingly, when you try to write down the Lagrangian, when you try to using electric field and magnetic field as our data to describe a system, we cannot do it. We have to using this some kind of very strange data, introducing this vector potential and scalar potential, using that to describe electric field and magnetic field. If you do that, then we can write down the phase space Lagrangian, or we can write down the Hamiltonian. And this actually is a very fundamental. The reason is following. You know, once we have a Hamiltonian, we can from here we can do quantum theory. So the fact that we cannot write down the Hamiltonian in terms of electric field and the magnetic field means that we have a difficulty to write down the quantum system using electric field and magnetic field. We cannot do that. In order to write down a quantum system which describes a particle in electric and magnetic field, we have to describe electric and magnetic field differently. We have to use vector potential and a scalar potential to describe electric and magnetic field. And then we can write down a quantum system. It's kind of amazing thing about the demand for quantum system. And so that seems to suggest that maybe scalar potential, vector potential is more fundamental. That's the information we need to write down a quantum system. And so this is quite interesting. This attempt to write down the Hamiltonian to describe a classical system reveals something pretty deep. You know, what is electric field? What is magnetic field? Yes.
So when you write it in terms of the potential, you still have a redundancy, right?
Exactly.
So your Hamiltonian is not uniquely defined, but it is not gauge invariant.
Exactly. I will come back to that. But you raised a very, very good question. You know, I'm really, really unhappy here. You know, E and B are perfect. There's no redundancy. They're just no gauge things, just perfect. But we cannot do it. We can induce something so ugly to write down quantum theory. But we are forced to introduce something ugly because we are forced to use Hamiltonian, because using Hamiltonian, we can go to quantum system. So this is I'm very unhappy about this. And so to write down quantum system, you have to use an ugly, redundant way to label your electric field, magnetic field. You cannot using a nice way to label using electric magnetic field to write down quantum system. You cannot do that. But why is that? Why nature requires something ugly? Yes?
But isn't it just an accident they look beautiful? Because if you look at E and B fields of general gauge theory, E and B fields are not getting married. It's only for the U1 case they are getting married. So
Yeah, but even for that's also true. For the non-abelian, it's even trickier. Yeah, and yeah. So but anyway, so what you have is really a very, very good question. I try to say in the physics are full of ugly things. Actually, all the people say there's a lot of beautiful things. But actually this is you know it's pretty unhappy. But certainly the reason I emphasize this point is following. Maybe later sometime you want to develop a theory like quantum theory, which don't have any gauge redundant thing. You know, this A and phi are not have this gauge redundancy. That's developing a theory without this gauge redundancy is much more natural. It's happier. And at the moment, we don't have that formulation. That's reflect the lack of understanding. And so maybe later we can have something better. So that gives us a motivation to do something better. Yeah. So, okay. So I actually spent a lot of time on this. Anyway, so actually this works. So let me just do a quick calculation to show it works. So let me just do this, you know, partial x, partial pi. And it's just plug in, just do it. It's just a math. It's a straightforward math. If you do this math, you just get, let me just copy things quickly. And this pi dot equal to minus partial h, partial xi. Yeah, here is a more complicated math. Let me do this partial. Okay, let me do partial I, AJ. So this shorthand, this partial I really means partial xi. Okay. So just some quick math. So if you make a derivative with the pi, here the only thing dependent on pi is here. So this square became this factor. Yeah. if you do the derivative with respect to xi, the easy part is we have something here that depends on xi. So we have this partial v, partial xi. But the a also depends on x. So there's some contribution from here. So you get this this factor back, then the partial ai. So here I assume the repeat index are sum. So this j is a sum. This I is a free index which match the I index here. So I assume this repeat index are summed automatically. Okay. So this is a pretty ugly equation, but I can put that in a nicer form. No, let me see. Let me see. This partial xi. Okay. So then we can try to do the following. So let's try to do this x double dot. We try to get the equation motion. We can try to get Newton's equation. So this is still unfamiliar. You know, this is something unfamiliar. It's something in equation motion in phase space. We are not usually write down that equation. So we usually write down F equal to ma. So that's Newton equation. So let's reduce this to the Newton equation. If you reduce this to the Newton equation, that became the pi dot minus partial I a partial j ai, then this xj dot, okay, over 2n. So we just make another derivative with respect to t here, okay. So we get this equation, and then we want to plug this p dot is here. This p dot, we just plug in the p dot. If you plug in p dot, what you get is m minus 1 minus partial I partial v plus pj minus aj over m partial I aj minus m inverse partial, this is j ai, and this pj minus aj m. Okay. So maybe let's don't do this. Let's just keep this as xj dot. Okay, let's keep this xj dot. So this term, this last term, just copy from here. I think so. Let me see. So I'm missing a factor 2 here. So the first term is that. No, no factor. I'm sorry. Yeah, let's just copy from here. Okay. So this still looks messy, but actually this form is not that messy, because this combination is let me try to see, this I or j. This is yeah, x dot j. Also x dot j is a velocity. So basically, now you can already see something like Lorentz force. There's something which is just a partial v, gradient for potential. That's a potential force. There's something depend on the velocity. This term and this term, the both terms depend on linear velocity. The contraction different. Here, this j contract with the aj. Here, this j contract with the derivative. So the way they contract slightly different. And but after all, it will be something, you can combine these two velocity terms together. You find this derivative aj and this derivative aj combined to magnetic field. So this just became something quite normal. So actually, this term can be written as a epsilon k, epsilon j I j k. So x dot j bk, basically. So by doing some kind of tensor index, so you can show that this is essentially equal to the Lorentz force, the velocity times the magnetic field, with a proper combination of index. Okay. And so indeed, this quantity is a produced particle in magnetic field. Okay. And so I'm very glad a student asked about this the gauge invariance. Because usually people don't talk about the gauge invariance issue. And it turns out that for our purpose, we have to deal with it. Actually, this gauge invariance later will appear, so we have to deal with it. So I have to discuss gauge invariance here. So what is gauge invariance? And so the gauge invariance is that the fact that if A if you let A change to A plus gradient AI, say, of some kind of function, and the phi changing to phi minus partial t lambda, then the equation motion will not change. So what is the equation motion? The equation motion is that mx double dot I equal to E times, so let's say E equal to 1, I, and epsilon ijk x dot j dk, where the B I equal to ijk partial j ak, and the E equal to minus ai dot minus gradient I phi. So this is a usual Newton's equation for particle in magnetic field and the electric field. And you can check that this equation motion do not change under this gauge transformation. It's very simple because this equation written in terms of B and E here. And the B and E do not change. The reason B do not change because when A making the derivative, changed by derivative of lambda, this B would change. The B would change. The delta B would be something like this epsilon ijk. We have derivative of j, and the A changed by something derivative of lambda, so there's a derivative of k lambda. So that's a change induced. But because this is antisymmetric, but these two derivatives commute, so this just always equal to 0. Okay, so you can using different vector potential and a different scalar potential to describe the same electric field and magnetic field, and equation motion do not change. So that's redundancy. So many different choices of vector potential and scalar potential actually describe the same electric and magnetic field, describe the same system. So that's many to one. We have many different choices of vector potential and gauge potential. They actually describe the same system. Very ugly. And but our phase space equation motion is even uglier. Look at this. If I change A by this gradient lambda, we have actual term here. And the actual term here, you know, and the V also changed. So it's all over the place. Lambda is all over the place. Equation motion totally changed. Not like this. Here is better. If I make a change, the E and the B don't change, and the equation motion remain the same. They don't change. So that's good. But here is really messy. And even though, and also our Hamiltonian changes as well. If you make A change, you know, there's an additional lambda term here. And there's additional lambda term here as well. So because phi also changes. So again, the Hamiltonian also changes. And so it's just a very unhappy situation. Now we have this different Hamiltonian that looks different, but somehow secretly when you obtain the equation motion at the last stage, they have to be the same kind of equation motion. They are the same. And yes. Yes. But however, I have to qualify. The very good way to put it. The gauge, you know, the trajectory in the phase space describe a different motion. What happens following? Here, this A and phi is my background field. For one choice A and phi, you have kind of trajectory. If I change A and phi, then the different trajectory would correspond to the previous trajectory. So let me say that this is a very good point. Suppose we have a phase space, we have a trajectory, and this phase space is A and phi. Okay. Then we have another system. But A and phi are changed by this gauge transformation. So let's call this phi tilt. This is like called A tilt. Okay. And then we have another trajectory. Then for some secret reason, these two trajectories have a one-to-one correspondence. And certainly, you know, there's another one and there's another one, and this one have a one-to-one correspondence. Yeah. So this is a gauge transformation in the phase space picture. It's not like that. It's that maybe these trajectories are independent of different choice. Like in this equation motion, the allowed equation, the motion do not change, do not depend on A and phi. So therefore, for A and phi, you have a trajectory. This corresponding trajectory have exactly the same shape. But here, they are not. But on the other hand, if you fix this background potential, then the different trajectory indeed describe different motion. If you fix this, so that's what really happens. So this really means. So actually, thank you for the question. That means how we fix the problem, because we believe there is such a redundancy here. We should see some kind of gauge invariance from here. You just say it's not invariant, it's very ugly. Certainly it's on the surface is that. But if you do things right, we should see there's something invariant there. And the key question to see the invariance is to this. When you choose different gauge, the trajectory also changes. So this pair of trajectory and background together, they make a correspondence. The trajectory change really means that this x and p may transform non-trivially under gauge transformation. That's a key. That's a point. And if you do that, we'll fix the problem. So then we can really this is this. Okay. So the key. So now because your question, we find a solution. The solution is that we have a transformation p. I has to change. Which is a p tilt, you can say. But x don't change. Just a p changes. So actually the whole Hamiltonian formalism would look better. You can see the gauge invariance if you also make a p change on the gauge transformation. And then the whole thing just getting nice and looks beautiful again. And so how to see that? So So let's first try to see the gauge invariance of a Hamiltonian. Why, or Lagrangian. So why Lagrangian is gauge invariant? Okay. So it's very important to introduce, it's called the gauge invariant potential, capital P, which is equal to Pi minus Ai. It's much more convenient to work with this capital P. It's called the gauge invariant momentum. Yes?
So originally when we started, we were treating P and X as degrees of freedom. Are we saying now we're introducing some P delta as a new degree of freedom that is empty?
No, it's a transformation. It's really trying to describe this kind of correspondence. That is if you change if you do the gauge transformation to the background potential, the path also changes, but they are corresponding. So basically, you can fix a gauge, and you have collection path that describe motion. You can choose another gauge, you have another collection path. But to compare these two gauges is a little non-trivial. You cannot compare the same path. This path in this gauge and this path in that gauge, they can be correspond. They are correspond to each other. So here I try to describe the correspondence. Basically, if you have a motion, basically, suppose I have motion pt xt, but under background of a and phi, this motion, this corresponds to a motion of a p tilde t, x tilde t, and the background of a tilde and phi tilde. So this is a correspondence. And I already described how a and phi change. So now this equation describes how x and p change. So actually x don't change, p change this way. Yes.
So is it just saying that we can map the two physically equivalent solutions to one another by this change of coordinates?
Yes. Exactly. So basically, suppose you have a solution for this background. Then using that map, you know that if this trajectory mapped using this transformation to another trajectory, the new trajectory will be a solution for the new background. So you'll see the how solution correspond to each other. Exactly. Yeah, exactly. Yeah. Yeah. So what is the same, what is different became gauge dependent. That is an amazing thing. You can see in this case, the position and the velocity itself a gauge invariant. When you have different gauge choice, you still have same position, same velocity. But the momentum itself is not gauge invariant. This is a thing. Momentum is not gauge invariant concept. If you think about that's quite amazing. Momentum is fake. This really tells us momentum is not gauge invariant. It's usually non-gauge invariant is unphysical. The saying momentum is unphysical is very uncomfortable. But this capital P is a gauge invariant. So this capital T is more physical. Anyway, so then the Lagrangian is a. So let me just write down the Lagrangian. Let's choosing phi because we assume E equal to 1. Okay. So this is our Lagrangian. Then I can write this Lagrangian in the capital P. If writing in the capital P is also is pretty simple. And there's an actual term, AI xi dot term. Yeah, this is actual term. Why? Because I'm sorry, this is really capital P. Okay. Okay. This term became this term. That's pretty obvious. Okay. And this is small p. This is big P. So small p, big p differ by a. So they differ by a times x dot. So that's a last term. Just cancel that difference. Certainly, why we do that? Because this one is gauge invariant. Look at this. If you do gauge transformations, little p gain a partial lambda. But the vector potential also gain the partial I lambda. So these two change cancel each other. So therefore, this combination is a gauge invariant. And so it's nice to write down the Lagrangian using the gauge invariant quantity. You know, here the capital P is gauge invariant, X is gauge invariant, X don't change. And so this is nice. Yes?
However, with this definition of the momentum, the gauge invariant momentum, we lost the correspondence between P being the conjugate momentum to X. I mean, this big P is no longer the conjugate momentum of X. Or is it?
No. So we do lose that. So this is the tension. The little p is a conjugate of X because this appearance, this is structure. But the big P is no longer because what's in front of X dot is this combination, big P plus A. So there's no happy solution in some sense. We have gauge invariance, so we lost conjugate interpretation. If we want the conjugation interpretation, we don't have gauge invariance. And so this is a fun story about describing a particle in magnetic field. Okay. So now first I want to show that this Lagrangian is a gauge invariant. So how do you show that? Because if you do gauge transformation, big P don't change. And this big P don't change, X don't change. But this one changes and this one changes. So Lagrangian is not really gauge invariant. So let's see how they change. You can see phi changing by something like partial T lambda. And no, I think this one probably don't change. Let me see. Yeah, I'm sorry. And yeah, this one probably don't change. Yeah, and but the A changing by something. If you look at how A changing by something partial I lambda. Okay, so that's how A changes. And but this change is coupled with xi dot. Okay. And this term, this combination gave us a partial T lambda. And two term cancels. Well, that's a lie. Actually, don't cancel. And be very careful. So don't take a note. And this partial T really means partial T. Remember, lambda is a function of xi and t. So this partial T means we take x fixed and the t changes. Really partial T. So this partial I lambda really make derivative with respect to x. Okay. So actually these two terms do combine. These two terms do combine. But they combine to something like a partial T lambda plus partial I lambda and xi dot. So this xi actually is a function of t. Because we have a trajectory, remember, this is about the trajectory. So this combination actually is a dt d lambda. So actually, the change from here and here don't cancel. But it gave you a total derivative. So actually, after transformation, this L goes to L plus dt d lambda, where lambda is a function for xi depend on t implicitly and also may depend on t explicitly. Okay. So this is how Hamiltonian changes. It's a total derivative. I'm sorry. It's changing by a total derivative. I cannot move that backward up. And okay. But that's not the problem. Because when the Lagrangian changing by a total derivative, there's redundancy. There's redundancy in the Lagrangian. We say that different Lagrangian describe different system. That's a lie, actually. If two Lagrangian differ by a total derivative, actually these two Lagrangian describe the same system because they all have same equation motion. You can check that, actually. If you change Lagrangian by a total time derivative, you will lead to same equation motion. Nothing really changes. Okay. So now they come to something quite funny. The Lagrangian have redundancy, which two Lagrangian differ by a total time derivative describe the same system. And this redundancy help us to understand the gauge invariance, because actually, if I allow the P to change like this, the phase space Lagrangian indeed is a gauge invariant up to a total derivative term. So up to this total time derivative term, the Lagrangian is invariant. So that's how we handle the gauge invariance property. And because time, I will not. You can really derive. You can write down equation motion in terms of big P and in terms of big P and X. You can get a gauge invariant equation motion. So I will not deriving that. But basically, the reason I discussed this really say that the canonical momentum is not gauge invariant. It's this strange combination is a gauge invariant momentum. And this one is more physical, but actually this one has physical meaning. This really is a m times x dot. So this one is the velocity. The actual velocity of a particle is not p, it's this combination. And so that's from this equation motion we already have over there. You can see on top of there. Sorry, this one here. That's that equation material. That's really the velocity. And so therefore, many times to writing things in terms of gauge invariant momentum would be helpful. You get something simpler, more physical. So that's basically the point. Okay, so that's a review of this phase space Lagrangian formulation, and it's a gauge dependence. So why we go through this? Well, because we want to derive. Maybe let me erase this. Because we want to derive classical equation motion from a quantum system. But you say how this Lagrangian formulation may help you? Well, it can. Actually, it's in a pretty simple way. So to see this, let's first write down this write down Schrödinger equation. So we know what is Schrödinger equation? Schrödinger equation is this. It's I d dt phi n t equal to h m phi m t. What is this? The Schrödinger equation, but in some strange point of view. Usually we write Schrödinger equation using the cat vector, you know. Here I say this cat vector, I just expand this cat vector using basis. You know, that's so this This phi just an amplitude of expansion. But now we have a very strange point of view. We view this phi, this amplitude, as a point in phase space. So this comes back to my first comment. What is state? State is a data which can characterize the system such that determine the state itself in the next moment. So actually, to describe a quantum system, the quantum state are characterized by a collection of data, which is a collection of complex number. So therefore, this PIRSA M is rather like this XP we talked about a moment ago. And this is very important. Actually, this correspondence is quite accurate. The amplitude of the wave function, or this expansion coefficient, corresponds to a point in the phase space. If you want to view quantum mechanics as classical system, this is really phase space. This is really phase space equation motion. It's very much like the equation motion you write down here. You know, it's a first order in time derivative. The first order time derivative equal to something. So we really can interpret this Schrödinger equation as a phase space equation motion. Okay. And certainly, this is just equation motion, but it also can be derived from the Lagrangian. The Lagrangian would be this. It's a phi m dot and a phi m. Phi is complex, so that's equal to this I phi m star phi m dot minus phi m star HMN. This big HMN is a big matrix that describes every quantum system, and that's it. So we view quantum system as a classical system, and it's Lagrangian quadratic, and have this form. Okay, and this phi and the phi star should be viewed as independent variable. That's as usual. The complex variable, the phi star independent. And then you can using this using the equation motion, you can using this Lagrangian equation motion, you can derive this Schrödinger equation. So basically from this partial L, say partial phi m minus d dt, partial L, partial phi m star. Let me put in star dot equal to 0, basically. And this equation will lead to this equation. Okay, basically, we don't have this term. There's no phi star dot. We don't have this term. We just have this phi term. We'll make a derivative of phi. You cancel this equal to that. So that's Schrödinger equation. Okay. So what? So the Schrödinger equation can be totally written in terms of so in terms of Lagrangian formulation. And and this one have a form. I can write in the bracket notation. Yes.
Your Lagrangian must be a real quantity, right?
Hmm?
Your Lagrangian must be a real quantity.
Here is not. But their integration, I think maybe its integration is real, because there's an I here. If you do the integral, you do the partial integral, that's probably is real. Yeah. And yeah, I haven't emphasized whether this should be real or not. This became a very interesting question, actually. Yeah. I think if you do the partial integral, this will be real. Not explicitly. So again, it's related to this total time derivative. This redundancy, this ambiguity part, may not be real. that is, you have this something with total time derivative. But if you have a if you do the integral, this total time derivative part drop out, then this action becomes real. Yeah. So I can write this as a I using this cat vector. It looks much nicer. So this is a Lagrangian. Okay. And this became very useful. So why this is useful? So let me just describe a general principle how we do it. So how to go from quantum to classical? So basically, this is quantum, because this is just Schrödinger equation. So this is a Lagrangian description of Schrödinger equation. But on the other hand, this form have some kind of classic analog. It's very much like the Lagrangian we use to describe the classical motion. Okay. So using this as a bridge, we can obtain a classical picture of a quantum system. So how do we do that? Well, so the idea is that we're using a trial wave function. Let me using this Kc. Okay. Maybe let's using this notation. Okay. So this Kc I is just a variational parameter. Okay. And for example, we have some Hamiltonian, and we write down some trial wave function where there's a Kc I, say Kc1, Kc2, just some variational parameter. And we want to using this to minimize energy. Okay, we do that all the time. Okay. But then after we minimize energy, then we get some kind of wave function of some shape or some wave packet or something like that. And then we try to see maybe this variational parameter can wiggle around. In a sense, if a Kc0, so suppose Kc0 is ground state, but if we shift Kc0 to some other value, it's no longer ground state. You know, if Kc0 is ground state, then Kc will not be ground state. If we start with something non-ground state, how this wave function would evolve? Certainly, when you have a ground state, it don't evolve. But if you have something not ground state, if Kc gets shifted away from the ground state value, it will evolve. But how they evolve? Well, according to Schrödinger equation. How they evolve according to Schrödinger equation. But here we make approximation. Remember, I'm using this Kc to describe a state. Okay, so different Kc describe different states. When I start with Kc, when this state evolve as when they evolve, then it goes to another state. But a new state, let's suppose we have this Kc, okay. And the next time it go to this Kc, it go to this Kc plus delta phi, okay. Some new states, just you add some state, okay. The trouble is that this new state cannot be written as Kasi with a shift Kasi. It cannot be. We cannot do that. The reason is that the state described by Kasi is a subspace of all Hilbert space, all possible vector space. And the time change may go out of this subspace. If they go out of this subspace, it's not expressible using this parameterized state. So we cannot do that. But in physics, we always do approximation. So the proposition here is that let's do it. So it's basically the following. We're using Kasi to label a subspace. Time evolution may go away from subspace. But approximation is let's project back to the subspace. Let's project back to subspace. So our approximation is that we assume we choose a pretty good parameter. So this subspace roughly describe the space of a motion. We try to consider the motion within this subspace. We always project back. And this gave us a motion within the space of a Kasi, and that's much simpler. Because our original system, the spaces can be huge. This Hamiltonian can be million by million dimension. But however, if you choose some nice parameter, only 2 parameters, then we only consider motion in this 2 parameter family. Then things become much simpler. So our phase space from million dimension to 2 dimension. Yes? Yeah, this is black arts. So basically, you need to understand the system properly to choose this properly. Otherwise, you get a bad approximation. So this requires understanding of the system. It's like choosing the variational trial wave function, very much like that. If you understand your system roughly, then you determine shape wave function more or less correct. Then this variational parameter just makes things a little more accurate. Yeah. Here we have the same thing. Here we have to choose this parameter properly so that you think this low motion at the low energy, because we're mainly interested in the motion in the low energy. We hopefully not only this Kasi give you ground state, but also give you first a few excited states. You kind of guess what is the space of a first a few excited states should be. We make a correct guess, and then this would give you pretty good approximation. Yeah. And but this is the key point. Instead of consider motion in the whole Hilbert space, we're using this called coherent states. We pick a class of states, a coherent states, and we consider motion in the subspace of coherent states. And whenever the motion go out of space, we project back. We force ourselves to live within this subspace. And then this give you, this coherent space is really, this space parameter by Kasi is like a phase space. You know, once you know the Kasi, you know next Kasi and etc. This is like phase space. So therefore, you're naturally operating the phase space motion. And to operate that would be very simple. Maybe I'm still let's using this. Let me put in Kasi. Let's put a Kasi to consistent with that notation. Okay. Let me put in Kasi here. Okay. So what is Lagrangian for that would be, let me just to end today's class, we'll just write down this. This is T dependence. And that's it. So this is a Lagrangian. Oh, I'm sorry, there's another term. It's also a T. This energy term. Okay. And this Lagrangian have the following form. Let me write down here. The first term have the form which is I. There's some kind of a function of a Kasi. I, then there's a Kasi I dot. You know, this is just taking first order derivative. So you just make a derivative, take overlap. So you get this form. And the second term is minus just the average of Hamiltonian, which is again the function of Cassey. Compared to something we're familiar with, or maybe let's drop this I. We can sub I in the A. We have a pi xi dot minus h, this classical theory. So the first term contains time derivative, first order time derivative, and some function of Cassey. This again has first time order derivative and the function of this phase space parameter. So these two are the same form. And then next term is total energy, which is average energy. So in this phase space, the first term is like this px dot term. The second term is energy term. And that's it. So this became a general recipe to obtain classical equation motion. Once you choose, so the key point is choose properly these variational states. Once you choose these proper variational states, and hope when you vary Cassey, this wave function describe this desired quantum fluctuation, quantum motion. You can see, for example, in the spin wave, you know, how should I choose Cassey? The Cassey should be the spin directions. In the spin wave, the spin orientation. And when you have the particle, how do you choose Cassey? It's a position wave packet. In your particle, you have wave packet. The wave packet may have different position, describe motion. If you choose this wave function as a wave packet, where Cassey is the center of the wave packet, then that describes motion. So there's many things one can do. But once you make this choice, plug in here, you get the phase space Lagrangian, and so that's a classical picture. Yeah. And so from here we can develop this how the particle moving in the band. That's how to go from particle to quantum to classical. How to from big matrix to the Newton's equation when you consider this band theory we just discussed last time. Okay, I will stop here. Yeah.